Hello students, welcome back to clariconcepts, unleashing conceptual learning. Today in this lecture, we are going to talk about Newton's law of viscosity. But before I move on to that particular topic, I would like to ask you several questions. Try an experiment. Think about you are traveling or you are running in open atmosphere in air on a road at let's say 40 kilometers per hour, and you want to run with the same speed in a pool of water, let's say in a swimming pool for example. Now can you imagine the difference of efforts that you need to apply when you run in water in comparison when you run in case of atmospheric air or on the road? What do you feel? In which of the two cases you will need to put more efforts on running at the same speed? Obviously you will say that, sir, in case of water, when I'm running in the pool of water, I need more and more efforts, right? Now question is, why is that? Why do you need to have more efforts in case of water when you are surrounded by the water molecules, and why it is that in comparison to this, when you are running in the air medium, when you are surrounded by the air molecules, you need less efforts? The answer to this question is provided by a property of fluid called viscosity, and the property has been clearly explained by Newton's. That's why the law that explains the property is called Newton's law of viscosity. And today in this lecture we are going to talk about Newton's law of viscosity in great detail, and we will also see the derivation and conceptual aspects of the same. So stay with us. So before I move on to that, let me perform an experiment. I have two different jars that you can see, and I have two different fluids filled in those jars, right? And what I will do is I have two empty beakers and I have a stopwatch. What I will do is I will try to tilt both this jar at the same angle for a same period of time, and we'll see that how much quantity of fluid is filled in both of these beakers. Let's do an experiment. So I'm tilting the jars at the same angle for a same period of time, and then I take them off. And what I've noticed is, in the left beaker I have more fluid filled, in the right beaker I have less fluid filled. So question is, why is that? The answer to this is, there is something which is resisting the flow of the fluid, right? And that something is nothing but the viscosity. So in case of right side's fluid, you can see the resistance should have been higher. That is the reason why the less quantity of fluid has been filled. And in the left beaker, the resistance of the fluid was lower comparison to this, and that is why the more quantity of fluid is filled over here. So I can say that the resistance is quantified by the term called viscosity. So viscosity is nothing but the measure of the internal resistance offered by the fluid to the flow. So what is viscosity? It is the measure of the internal resistance offered by the fluid itself to the flow. So you can say that viscosity of this particular fluid is higher and viscosity of this particular fluid is lower. So you can say more the resistance, more is the viscosity, or higher is the viscosity. Now the question is, you can easily compare the two liquid and say that, okay, this liquid is highly viscous, this liquid is highly, relatively low viscous, right? My question is, how do you quantify that? Right now you can easily see the difference, that's why you can compare. Now when the two different fluids are very, very close enough, now how do you quantify the viscosity, right? And how it is defined? So today let us talk about that. Now before going to the definition, we would like to talk about Newton's law of viscosity, from where the viscosity has came out, and for that we will perform another experiment. Let's say I have the physical upper plate and I have the lower plate, and between these two plates I have the fluid filled between these two, wherein I allow, I try to apply the shear force on the upper plate of the magnitude, let's say F newtons, and keeping lower plates fixed. Now in this experiment, I assume that the bottom layer of the fluid is glued to the lower plate of the, the upper layer of the lower plate, and the upper layer of the fluid is glued to the upper plate. That means there is no relative motion between the bottom layer of the fluid and the lower plate. Also there is no relative motion between the upper layer of the fluid and the upper plate. That means there is no slip, right? Now what will happen with this is, when you apply the force, the fluid will start deforming. And we have seen in that lecture of fluid definition, where fluid is a substance which keep on deforming continuously under the action of shear force. That is how it is defined. Now when you apply the shear force F, and if you keep on applying this force F, what will happen is, this upper plate will keep on moving, this fluid layer will keep on deforming, and then the upper plate will reach at a particular velocity called V meters per second. But the lower plate is fixed, it will not move, right? Now that means what? That means the upper layer, the topmost layer of the fluid which is in contact with the upper plate will also move with the same velocity V meter per second, and the bottommost layer of the fluid is attached to the lower plate, and therefore the bottom layer has zero velocity. Now if you try to locate several points, Let me look at the front view, and I'm showing you the front view of the same experiment. These are the two plates, lower plate, upper plate, and there is a fluid medium in between. Where upper plate is, stress, the shear force F is applied to the upper plate, and upper plate moves with velocity v meter per second. The distance between the two plates, let's say it is L meters, for example. Now, when you try to locate several points in between, let's say this bottommost point and the topmost point are the two boundaries. So, topmost point is in touch with the upper plate, the bottommost point is in touch with the lower plate. And now, when you locate the vertical line joining all these 4 points at some instant of time, let's say t equal to 0. Now, what you do is you try to observe all these 4 points and their position in certain interval of time, let's say dt. So, let's see what will happen. What have you observed? In a time dt, the topmost particle which was in contact with the upper plate has moved a larger distance, and relatively if you look at all the other points, the distance travelled by these points have been reducing from top to bottom, and the bottom point has not moved at all. It means what? The velocity of this point is 0. Now, if you join this line, all these points with a line, you will see that the angle shift, the shift in the angle that is observed is d beta. Let's say the small angular shift has been observed, it is d beta. Now, if you try to draw the velocity profile in the fluid layer, you will observe that the velocity of this particular point is the highest. That's why it is v meter per second. And when you come down from the top, the velocity will keep on reducing, and at the bottommost point, velocity will be 0. Right? Now, let me show you in general that let us suppose from bottom at a distance of y meter, the velocity profile, the velocity of a fluid layer which is located at a distance of y meter from the bottom is, let's say, u meter per second, somewhere like here, right? And if I try to denote this triangle, two different triangles, one is this, that is A, B and C, and another is this A, D and E, for example. Now see, what I'm trying to do here is, I'm trying to make you understand about the Newton's law of viscosity and the law from where viscosity came about, right? Now let me just explain you keep on this triangle. Now let us say this particular point, this particular particle, it was at this position at t equal to 0, it came to this position at t equals to dt. That means in the interval of time dt, it has travelled how much distance? Let me mark the distance. This is the distance travelled, and let us suppose distance is around, let's say, dA. A small distance dA is travelled. So if I look at this triangle, let's say triangle F, G and H, for example, can I say tan d beta? Tan of d beta equals to opposite by adjacent. So in triangle F, G, H, tan of d beta is equals to, I could say, dA, that is opposite divided by adjacent, that is L. Now what is dA? dA is the distance travelled by this particle who has velocity v meter per second in time dt. So can I say that velocity of particle is what? Distance travelled by time taken. So can I say that this dA is nothing but velocity times dt, or else you can say v equals to distance by time. dA by dt, time taken from here to here is dt, and the velocity of the particle is v. So v is said to be distance travelled dA divided by t, and if you want dA, you can multiply dt over here, you will get the v times dt is the dA. So what you will do is, this dA will be replaced by v into dt divided by L. L is as it is. Now what is tan d beta? See, the time interval between these two is 0 and dt. So dt is very small interval of time, and I hope you are aware about this trigonometric rule that for a smaller time, I am sure that the angle d beta will also be very small, and for a smaller angle d beta, you can replace this tan d beta to be equals to just d beta. Why? For a smaller values of d beta, I could say that tan of d beta is equals to, it is approximately equals to d beta itself, right? That means what? D beta by dt is equals to v by L. This is equation number 1, let's say. Now what is d beta by dt? Do you know? In real sense, d beta is the angular shift, it is shear strain, dt is the time taken of the shear strain. So you can say d beta by dt is the rate of shear strain, right? Now from triangle this ADE and triangle ABC, because both of these are similar triangles, so based on similar triangle property, can I say u divided by y is equals to v divided by L? See, again I am saying, in triangle ADE and triangle ABC, can I say, because they are similar triangles as per the trigonometric rule, U divided by Y should be equals to V, that much is distance, divided by this L. Yes. So from similar triangles, triangle A, B, C and triangle A, D, E, I would say U divided by Y is equals to V divided by L. So you will put Y on the right hand side, you will get U is equals to V by L into Y. Now you see, you look at this equation, this equation is giving you the velocity profile. How? At different values of Y, you will get the values of U. So if you put Y equal to 0, Y equal to 0 is at the bottom point. So your velocity should be 0. You put Y equal to 0 over here, you will get U is 0, velocity is 0. If you put Y equals to, let's say, L, capital L, at the topmost layer, you should get U equals to V. Let us check. Y equals to capital L will get cancelled, U equals to V. So this is velocity profile. Now if I derivate this, if I differentiate this equation with respect to Y, what I will get is du by dy. V by L is constant. V by L is constant. It is not changing with respect to Y, right? You can take it outside. Differentiation of Y with respect to Y, dy by dy is 1. So you will just put 1. So what you will get is du by dy is equals to V by L. Let us suppose this equation number 2. Now see what I am trying to do. Look at 1 and 2. Can I write from equation 1 and 2 d beta by dt is equals to V by L is equals to du by dy. This implies, can I say d beta by dt is directly equals to du by dy. So du by dy is nothing but the rate of shear strain, yes or no? This is the equation number 3, let us suppose. Now why I am doing this, why I derived this equation, because experimentally it is proven that, when Newton did several experiments, experimentally it is proven that shear stress on any fluid layer is directly proportional to the rate of shear strain of that fluid layer. And when Newton did experiments, he said that if you want to remove the sign of proportionality, you will have to add a proportionality constant, and in this case, that proportionality constant is nothing but the viscosity mu of the fluid. So here is where the viscosity has been introduced by Newton, and he said that this viscosity mu is also known as dynamic viscosity, right, many a times. So don't get confused in that. So mu is the proportionality constant which refers to the fluid property called viscosity, and that refers to the resistance offered by the fluid. Okay. Now from equation number 3, can I say d beta by dt is nothing but du by dy? So I can replace d beta by dt with the term du by dy, and here is the final form of Newton's law of viscosity. What does it says? Let me explain you. It says that tau is what? Shear stress at any fluid layer. It says that shear stress at any fluid layer is equals to viscosity multiplied by, what is this u? It is viscosity. Viscosity of the fluid, or you can say dynamic viscosity. Both of these names are same. Just viscosity or dynamic viscosity, right? Shear stress at any fluid layer is equals to viscosity times the rate of shear strain at that particular fluid layer. What is this? Du by dy is referred as rate of shear strain. Clear? Understood? Let us now talk about the units of this viscosity. But before I move on to the units, let me share you that the tau that we have seen is on the, let's say, top layer. If I talk about the topmost layer, the tau that I will see is on the fluid layer, right? And what is this tau? Can I say this tau is equals to the shear force divided by the area? This area is, let's say, A. The area of this fluid layer is A, for example. So if the equation says like this, tau equals to mu du by dy. I'm just explaining you the concept of mu, right? So what can I say? Mu should be equals to what? Tau divided by du by dy. If you still simplify this, what you will get? What is tau? Tau is shear stress on the fluid layer. It can also be said as the resistive force F divided by the area, because stress is force by area, shear force divided by area. Divided by, what is du by dy? Du by dy, we have also seen that it is equals to V by L in the derivation. Du by dy is V by L. So I'll just put V by L here. So when you look at this expression, you will get shear force divided by, if you put A on the bottom denominator, V by L. Now you see, what does it mean? How is viscosity defined? It is defined as the shear force required. Shear force required to move the upper plate at a velocity which is 1 meter per second. If you put V equals to 1 meter per second, length equals to 1 meter and area equals to 1 meter square. What does it mean? See, length is 1 meter, that means the distance between the two plates is 1 meter. Area is 1 meter square, means the top area is 1 meter square, and velocity that the plate moves is 1 meter per second. That means what? If the viscosity is what? Viscosity is defined as the shear force required to move this plate at 1 meter per second when the plates are separated by a distance of 1 meter, when the fluid is filled between these two plates by a distance of 1 meter, and the contact area is 1 meter square. So I hope you got the definition now of viscosity, right? So that is the shear force. Particularly for case of water, it is 1 centimeter. So let us talk about the units of viscosity first to understand more about it. So units of viscosity. See, I know that mu is equals to tau divided by du by dy, right? So unit of mu should be equals to what? SI unit of mu. I would write SI unit of mu should be equals to SI unit of tau divided by SI unit of du by dy. Yes. So what is SI unit of tau? It is Pascal, or you can say Newton per meter square. What is SI unit of du? Du is in meter, change in velocity, meter per second, and you have meter over here, meter per second into 1 over meter, right? Dy is change in distance, that is this cancelled. What is Pascal? Newton per meter square, and you have this 1 over second. Second will go up, meter square will come down. So Newton second per meter square. This is one unit of SI unit of viscosity. Number one. You can still further, rearrange this. So you can say that SI unit of mu, you can still represent Newton in terms of kg and meter per second square. So this is Newton second per meter square. You know, Newton can be rearranged in terms of mass into acceleration, meter per second square. Newton is a unit of force, right? Force is mass into acceleration. And if you put like this, you will get, second will get cancelled, and 1 meter will get cancelled. So you will remain with this kg per meter second. This is SI, another SI unit. Another SI unit of mu, right? Many a times, mu is also referred as the CGS unit. So I would say CGS unit of mu. What is CGS? You see, CGS means what? Centimeter, gram and second. So mass is measured in length is measured in centimeter, weight is measured in gram, mass is measured in gram, and time is measured in second. So kg meter per second was SI unit. So kg is the unit of mass, right? So here in CGS you will put that gram, just gram. Meter you will put in centimeter, and the second you will put it in second, just. So gram per centimeter second is the CGS unit of mu, and this is also known as poise. This is also known as poise, right? Now, many times in numerical, it may happen that you have been given the value in poise, and when you use the Newton's law of viscosity, you need to put the value in SI unit. So you need to have the conversion between these two. So let me talk about the conversion. Just a minute. Let me talk about the conversion. It is very, very essential. So if I say 1 kg per meter second, if I want to convert this into poise or gram per centimeter second, how do I do that? Kg, if I use 1 kg is how many grams? It is 1000 gram. 1 kg is 1000 gram. 1 meter is 100 centimeter. And 1 second is 1 second. Simple. So you got the answer. So this is 10 gram per centimeter second. 1 kg per meter second is what? 10 gram per centimeter second. Also you can say 1 kg per meter second is also 10 poise. So what does it mean? It means that whenever you have been given in numerical that so and so fluid has viscosity of 15 poise, and if you want to convert that into into SI unit, you need to divide it by 10. Why? Because you see 1 kg per meter second is 10. So 1 time this will make 10 times this. So what is poise? So if you take it reverse, I can say 1 poise is equals to 1 by 10 kg per meter second. So 15 poise will be 15 by 10 kg per meter second. So whenever you have been given value in poise and you want it to be in SI units, you need to divide it by 10. always. And whenever you want to convert from SI to CGS, you need to multiply by time. So let's say 2 kg per meter second is 20 poise, simple, right? So keep this in mind. So I hope you have understood this. Thank you so much. We'll see you in the next class where I'll talk about the another property of the fluid called kinematic viscosity. Thank you.